Hello, I am the magnanimous Mr. Daycock, and today I am going to be giving you some further examples of solving non-homogeneous first-order recurrence relations. So last time we looked at this one, and we established that what we needed to do was rearrange it slightly, so we had the homogeneous part entirely on one side, and the non-homogeneous part entirely on the other. And then what we had to do was split it into two parts. The complementary function, which solved our homogeneous part equal to 0, to solve because we can always think of it as add 0, and the particular solution, which solved our homogeneous part equal to the non-homogeneous part, the n minus 2. And solving each of those was done in different ways. For the complementary function, we just solved it in the standard way, the way we'd usually expect, and spotted that this is lots and lots and lots of multiples of 4, so it's just going to be c times by 4 to the n. And then for the particular solution, we went, well, we need something that looks like this, and so I'm going to pick an plus b as something that looks like the non-homogeneous part to get that when we plug it in. And then to solve this one was pretty much solved already. To solve this one over here, so the complementary function was pretty much solved already. To solve the particular solution, we just plugged that in to our recurrence relation, and that would give us our answer, or at least give us the coefficients of a and b. And then lastly, we would get an answer of the form un was equal to the sum of these two things, so c times 4 to the n, plus our an plus b, but in this point the a and the b would have been found. And then we just plug in our initial condition to find the c. And that would give us our complete solution. Oh, excuse me. Now, let's use this into another example. So here, this is a very, very similar example. So we want our complementary function first, which from this we're dealing with un minus 4 lots of un minus 1 equal to 0, and that gives us a complementary function of c times by 4 to the n, just like before, because this is a very similar problem. For our particular solution, we just want our un minus 4 un minus 1 to be equal to just n. And so it's at this point very tempting to plug in an as our attempt. But this actually won't be good enough, because for the un minus 1 we will actually get a constant as well, and that won't disappear, which we need it to, because this point here is empty. We need that constant to disappear, and so we actually need to include a constant always to ensure that that constant we get from this term disappears. So we basically, when it comes to this, if we're dealing with some kind of polynomial, in this case this is n to the power of 1, or if it could have n to the power of 2 or n to the power of 3, you need to have whatever the highest power is, in this case 1, plus every term lower. So in this case, we also need the constant term, which is n to the power of 0. So we try that, plug it in. We know that if this is un, then un minus 1 must be the same thing, but with n minus 1n. Plug both of those in, and we're going to end up with an plus b minus 4 lots of an minus 1 plus b equal to un minus 1. And we expanded this last time, and we're going to get something very similar. We're going to get minus 3an. In fact, it's going to be exactly the same on this side. So that's not un minus 1, that's just n. Let's remember that. And for our constant term, we're going to end up with plus 4a minus 3b. And that still equals n. And now, matching up our coefficients of our n term, we still have minus 3a is equal to 1. And the coefficient of our constant term Well, we have 4a minus 3b equals 0 in this case. Solving that, we still get a equals negative 1/3. And over here, plugging that back in, we get negative 4/3 minus 3b equals 0. Kind of like 6. Pushing that over, we get minus 3b is equal to 4/3, positive 4/3. And that gives us b is equal to negative 4/9. And so now, in this case, slightly different, our particular solution is equal to negative 1/3 of n minus 4/9, which is slightly different to last time, despite it being a very similar question. And therefore, our general solution, being equal to the complementary function plus the particular solution, gives us un is equal to c times by 4 to the n minus 1/3 of n minus 4/9. And then we just want to find out what c is. So we go back to the top and ask ourselves, what was our initial condition? When n equals 1, our sequence was 5. So we plug in n equals 1, and we get 5 is equal to 4c minus 1/3, because if we plug in 1 into 1/3, we get 1/3 n, we just get 1/3, minus 4/9. And that will give us, so minus 1/3 is 3/9, this is 7/9, and we're going to end up with 52 over 9 is equal to 4c, and so c is equal to 13 over 9. And this gives us our general solution of un is equal to 13 over 9, lots of 4 to the n, minus 1/3 n minus 4/9. And notice we did need that constant on the end for our particular solution, otherwise we would not have got the correct answer. Okay, next example. Up here we have got un is equal to 2 un minus 1 plus 4 times by 3 to the n. Exactly the same thing. Our complementary function needs to solve just un minus 2 lots of un minus 1 equal to 0, and that is going to be something in the form c times by 2 to the power of n. Our particular solution, we need to try un equal to something that looks like this. And the thing that matters, the coefficients in front don't matter. That's in fact the thing that changes. So we need something that looks like 3 to the n. So we're just going to try c times by 3 to the n. And then we're going to plug that in. We still need what un minus 1 is. So un minus 1 is equal to c times by 3 to the n minus 1, which isn't actually a helpful form. So we need to think of this as c times by 3 to the power of n times by 3 to the power of minus 1, using our multiplication rules. And 3 to the power of minus 1 is 1/3. So we need to think of this as c over 3 times by 3 to the n. And that is going to be a useful form because we've got everything will be in terms of 3 to the n. And then we plug it in. So we're going to get, plugging it into our formula, which we're dealing with is un minus 2 un minus 1 is equal to 4 lots of 3 to the n. We're going to get un is just c times 3 to the n. Oh, I apologise, I shouldn't be using c in all of these cases because we've already used c. Let's put that as k. And so we're going to get k times by 3 to the n, because that is what un is, or at least what we're trying for un, minus 2k over 3, because remember this was k over 3 for this one here, times by 3 to the n, equal to 4 lots of 3 to the n. And if we notice there's a 3 to the n in every single term, that can never be 0, so we can just divide through by 3 to the n. And we end up with k minus 2k over 3 is equal to 4. Or in this term, you can think of this as taking coefficients of 3 to the n. Either way, you end up with the same thing. And then we get 1/3 of k is equal to 4. and so k is equal to 12. And so our general solution is again the complementary function plus the particular solution. So in this case, it's going to be un is equal to c lots of 2 to the n plus 12 lots of 3 to the power of n. And then we need to plug in our initial condition, which is u1 equals 1. So 1 is equal to c times by 2 to the power of 1 is 2c. 12 times by 3 to the power of 1 is 36. And we get that 2c is equal to negative 35, and c is equal to negative 35 over 2, which gives us our final solution of un is equal to negative 35 over 2 times by 2 to the n, plus 12 times by 3 to the n. And we can make this very slightly nicer, because notice here, there is a power of 2 here. So what we can do is we can include that in here. And this is a negative power of 2. This is 2 to the negative 1 because it's on the denominator. And so this can also be written as un is equal to 12 lots of 3 to the n, moving the positive term to the front, minus 35 times by 2 to the n minus 1. And that is a closed form in purely integer form for our recurrence relation. Okay, and let's go over here to one more example. This is similar to the other ones, except notice that our non-homogeneous part is purely a constant in this case. So our complementary function, just as before, is going to be of the form c times by 6 to the n. Our particular solution, now, well, we don't have any n's, but we do have a constant. So we need to pick un equal to some constant k. And equally, in this case, our un minus 1, or in this case, let's be careful, it's using un plus 1. Our un plus 1 must also be equal to k, because that's almost the definition of a constant. If something is constant, it stays the same. And then we plug that in to find out what k is. So we're going to get k minus 6k is equal to 3, and we get minus 5k equals 3, and so k is equal to minus 3 over 5. Our general solution is then un is equal to c times by 6 to the n minus 3/5, and we just need to plug in our initial condition, which is when n equals 0, un is 2, so 2 is equal to 6 to the power of 0 is 1, c minus 3 over 5, and that means that c is equal to 13/5. And so we get our general solution of un is equal to 13/5 times by 6 to the n minus 3/5. Okay, and there you go. There are 3 examples right there of various problems using your non-homogeneous part. And lastly, I just want to give you a little bit of a table of examples and what type of function you would use. So here's your examples, and here's the particular solution you would try. So if you've got just some constant like 4, then you would try un equals k, just some constant. If you've got 3n plus 4, then you try un is equal to, doesn't look like an n, un is equal to an plus b. Equally, if it was just, say, 7n, then again you would still use un is equal to an plus b. If it was on the form, let's make that clearly an n, n squared plus 3n, then you'd use something like un is equal to an squared plus bn plus c, just making sure you get everything in there, including a constant, even though there isn't one here. And lastly, if you have it of something like this, where it's just like 4 times by 7 to the power of n, then you try un was equal to just some multiple k times by 7 to the n. And there you go. Those are all the particular solutions you would try for various different examples. Okay, thank you very much, And next time we're going to look at a very slightly more complicated situation. Thank you very much for watching. See you next time.